Hi, in the second section of the logic lecture, we discuss quantificational logic, sometimes also called predicate logic. We will skip most of the theoretical considerations and focus mostly on aspects connected to using quantificational logic formulae. The objective is that you be able to read, understand, and write quantificational logic. Quantificational logic is so called because it includes the two so-called quantifiers, written as a rotated A and E. Their job is to introduce and bind variables that the rest of the formula may depend on. The rotated A is the universal quantifier and is read for all. A universally quantified formula is true if it is true for all the values that can be bound to its variable. Similarly, the rotated E is the existential quantifier. It is read as exists, and an existentially quantified formula is true if there is at least one value that, when bound to the variable of the existential quantifier, will make the rest of the formula true. In order to determine the value of a quantification formula, one usually has to know which set of values the quantifiers quantify their variables over. That is, which values the variables can be bound to. Let's look at some examples. This one can be read as, for all x, there exists a y, such that x and y are coprime. Clearly, for this to make sense, we need to assume that the variables are quantified over the integers or the natural numbers. When unambiguous, we can also drop the parentheses. If you want to represent formulae that depend on parameters, we sometimes use this kind of prefix syntax. Here, C is a logic formula with two parameters. It's a bit like a function, except that instead of computing a value, it is either true or false. Such parametric logic formulae are also sometimes called predicates. Of course, in order to properly interpret this formula, we would need to know what C means and how many parameters it takes, in this case 2. Here are a few logic formula examples from the textbook. Again, for them to make sense, one needs to make reasonable assumptions about the meaning of the predicate symbols. In most practical applications, we really want to quantify over a specific set. The set of all strings of zeros and ones, some inductively defined closure, for example, the natural numbers, etc. We can introduce quantifiers that do so as syntactic sugar, like this. With that, let's look at the truth or falsehood of a few quantified formulae. And these are the answers. How would you write these two propositions more explicitly using quantificational logic? In the second formula, where n is supposed to be an element of the set of prime numbers, it might be helpful to use the set n2 of natural numbers greater or equal to 2. And these are two possible answers. Since in many cases more than one variable is quantified at the same time over the same set, we can also use a bit more syntactic sugar to introduce them simultaneously with a single quantifier. Are these formulae true or false? And these are the answers. How would you express that a relation is transitive in quantificational logic? These are some possible answers. For some more practice, try to take a look at the axioms of set theory and see if you can understand what they are saying. In particular, have a look at the axioms for extensionality, infinity, and power set. Keep in mind that in axiomatic set theory, absolutely everything is a set. Also, the construction S of y in the axiom of infinity is something you might have encountered before, as von Neumann numbers. When the set that variables are quantified over is finite, one can replace a universal quantifier with a chain of conjunctions and an existential quantifier with a chain of disjunctions, effectively transforming a quantificational formula into a propositional one. It's similar to loop unrolling, a program transformation in which bounded loops are replaced by copy-pasting the loop body the appropriate number of times, replacing the loop variable with a corresponding constant. Do a finite transform for this little formula, assuming that its variables are quantified over a two-element set with elements A and B. For any two formulae alpha and beta, it is always true that the conjunction distributes over the universal quantifier and the disjunction over the existential quantifier. It might help to see this if you imagine what this would look like for finite transforms. Also, for any formula, these equivalences hold, which allow you to flip existential quantifiers into universal ones and vice versa. Here, it might help to recall De Morgan's laws. When reading logic formulae, it is important to keep track of the scopes of the variables, which work like they do for most programming languages. A variable that is introduced by a quantifier is bound by that quantifier within the scope of the formula that follows it, unless inside that formula that same variable is bound again by a quantifier. For example, this is the scope of the y bound by the existential quantifier. This is the scope of the universally quantified x. This that of another universally quantified x, and this that of an existentially quantified z. Looking at the locations where quantified variables are used, these are the bound variable uses, and the quantifiers they are bound by. Which means that these two occurrences of the variable y are not bound by any quantifier. Therefore, y is what's called a free variable of this formula. So, in summary, we call a variable occurrence bound if it occurs within the scope of a quantifier binding it. If there isn't one, the variable is free. A formula that doesn't contain any free quantified variables is called a closed formula, or sometimes a sentence. Another equivalence among logic formulae pertains to the case where a quantifier introduces a variable that isn't actually used in the formula, in which case the presence of the quantifier makes no difference either way. This doesn't work in the rather abnormal case when the set that is being quantified over is empty. So little care must be taken to ensure that that isn't the case. Also, one can rename a variable inside a formula with another name, as long as that new name does not occur anywhere else in the formula. In order to interpret a formula, that is, in order to determine whether it is true or false, we need to interpret every symbol in it, and we also need to specify which values the quantified variables in it can assume. That is, what set of values the quantifiers actually quantify over. That set is called the domain, sometimes also universe, for interpreting the formula. Let's call it D. An interpretation of quantificational logic is a function that assigns the various parts of the formula mathematical objects. Constant symbols and variables, for example, are mapped directly to elements in D. Function symbols with n arguments are mapped to functions from D to the n to D. And those prefix relation letters representing predicates are mapped to subsets of D to the n, with n being their arity. With that, we can evaluate terms using recursion on their structure. And the same with formulae. This is very similar to other kinds of structurally recursive evaluation we have encountered before, except that it also needs to process the quantifiers. A detailed discussion of this is beyond the scope of this course, but if you're interested, you'll find a discussion of techniques for interpreting quantifiers in the textbook. For our purposes, it shall suffice to have an understanding of the meaning of quantified formulae, and that there is an interpretation that assigns quantificational formulae a truth value. Just as we did for propositional logic, the notion of an interpretation allows us to be specific about logical implication and logical equivalence between quantificational formulae. And just as we did before, we say that a set of formulae A logically imply a formula B, beta, if there is no interpretation such that all the formulae in A are true under it, but beta is false. And also, as for propositional logic, two formulae are logically equivalent if they logically imply each other. A formula that is implied by nothing is called logically true. A formula whose negation is logically true is a contradiction. And, also as before, a formula that is neither is called contingent.